In this video, we're going to look at changes of momentum and how they are related to the resultant force acting on the object. Pause the video and do these 5 questions. Press play once you've done them. You should have now done these 5 questions. Please mark them as I go through them. So Newton's first law, otherwise known as the law of inertia, says that an object will continue doing what it's doing unless a resultant force acts. So an object will continue at constant velocity. That includes a constant velocity of 0, so not moving. So it could continue not moving unless a resultant force acts. Remember, velocity is what type of quantity? Say your answer to the video. You should have said that velocity is a vector quantity. So therefore, a constant velocity means a constant speed and a constant what? And a constant direction. So an object will continue at a constant speed in a constant direction unless a resultant force acts. So if a resultant force does act, what will that do to the object? Say your answer to the video. If a resultant force does act, that will make the object accelerate, which could mean change speed or change direction. Now, the next question just uses some equations that we've done previously. So finding acceleration, so that uses A is change in velocity over time. So we use V minus U over T. So V is the final velocity, which is 3.8. U is the initial velocity, which is 10.6. And the time is 6. You're always allowed to use a calculator in physics. So 3.8 minus 10.6, that's minus 6.8. So that's the change in velocity. The minus shows that it's slowed down. Divided by 6 gives minus 1.13. And then the units of acceleration are meters per second squared. For part B, we're finding the resultant force. So for that, we use resultant force is mass times acceleration. That's related to Newton's second law. So 150 times the acceleration that we just worked out. So we times our answer to part A by 150, and that gives minus 170. I used the non-rounded value from my calculator, and that's why I got exactly minus 170. And finally, the change in momentum. So I need to work out the momentum at the start. So P at the start. So that was mass times the original velocity. That was 150 times 10.6. And then I need to work out the momentum at the end. So that's the mass times the velocity at the end. So that's 150 times 3.8. I'll work both of those out with a calculator. So 150 times 10.6 is 1,590 kilogram meters per second. 150 times 3.8 is 570 kilogram meters per second. So finding the difference, so do 570 minus 1,590 gives minus 1,020. Again, the minus shows that it's slowed down. Please mark those answers. Press play once you've marked them. You should have now marked these answers. Let's go through these ones now. So for part A, the distance traveled in the first 2 seconds. So finding distance from a velocity time graph, you find the area under the graph. So I'm finding the area which I've shaded in blue. So this area here. So that area is going to be, it's a triangle. So base times height over 2. So 2 times 30 over 2, which is going to be 30 meters. Part B, I need to find the distance traveled in the second section. So that's between 2 and 5 seconds. So that's the area of this part here. So that's going to be a base of 3 and a height of 30. It's just a rectangle, so that gives 90 meters. And finally, section C, I need to find the distance traveled between 5 and 8 seconds. So you need to find the whole area under the line between 5 and 8 seconds. Now that is a compound shape, it's a trapezium. So I'm going to split that up into a triangle and a rectangle and just add those together. So the rectangle part has a base of 3 and a height of 30, which is 90. And the triangle part has a base of 3, a height of 20, so base times height over 2, that's 60 over 2, which is 30. Add them together, gives 120 meters. So the total distance traveled on that whole journey, I'd add all of those together. So that'll be 120 plus 30 plus 90, which is 240 meters. Defining stopping distance, well, stopping distance is the sum of the thinking distance. So that is the time. So in the time that it takes to react, in the reaction time, if you do reaction time times speed, that gives you the thinking distance. So that's the distance that you travel in the time it takes for you to react to the problem in the road, plus the braking distance. So that's the distance that you travel from the moment that you press the brake until the moment that you stop. Finally, how and why does tiredness affect stopping distance? So for the how part, you need to say, does it increase or decrease it? So it will increase stopping distance. And for the why part, you need to link it to the definition of stopping distance. So it increases the stopping distance because tiredness will basically slow you down. It's going to slow down your reaction time. So because tiredness will increase your reaction time, so tiredness will increase your reaction time and therefore your thinking distance. So the idea is that it's your thinking distance that's increased, and that causes the braking distance. Sorry, that does not cause the braking distance to increase. It's your thinking distance which increases, which causes the stopping distance to increase. So remember, there's different factors that affect the different things. Thinking distance is affected by anything that increases your reaction time. So tiredness, distractions, drugs, alcohol, whereas braking distance is increased by anything that affects the slowdown once you press the brake. So that is anything to do with the roads, so icy or wet roads, or anything to do with a car, so faulty tires or faulty brakes. So let's have a look at changes in momentum. So imagine you drop an egg. So here is an egg, and you drop the egg onto a hard floor. What's going to happen? The egg will crack. Whereas if you drop an egg onto a nice soft pillow, it's a nice soft pillow, it will land comfortably and will not crack. Now, both of those eggs have the same mass, let's call that m, and they're both going to hit the surface at the same velocity, let's call that v. So the question that we're going to be dealing with is, why does this egg crack and this egg does not? If they're both traveling at the same velocity when they hit the surface, they're both going to experience the same change in momentum. Both eggs are going to slow down from the speed they were moving at to 0, and they both have the same mass. So both eggs will experience the same change in momentum. They're both going to slow down from whatever speed they're moving at to 0. So why will one egg crack and one will not? So obviously it has something to do with the surface, but we need to really understand why. And we're going to do that by linking resultant force to momentum. So resultant forces cause changes in momentum. We've already studied that resultant forces cause what? Think about Newton's second law. Say your answer to the video. Resultant forces cause acceleration, and acceleration can mean changes in two different things. What are those two different things? Say your answer to the video. So acceleration can mean a change in speed or a change in direction. So if a resultant force causes a change in speed, that changes your momentum. Also, momentum is a vector quantity. So if resultant force changes your direction, that also changes your momentum. So by definition, resultant forces, because they change your velocity, also change your momentum. So what we're going to do is understand the link between the resultant force and the change in momentum that happens. And we're going to do that by using two equations which we already know. So here's the first one, F equals ma. So resultant force equals mass times acceleration. So resultant force is mass times acceleration. What are the units of those quantities? What are the units of resultant force? Say your answer to the video. You should have said newtons. What are the units of mass? Kilograms. And what are the units of acceleration? Meters per second squared. The other equation which we're going to use is the equation for acceleration. So acceleration is change in velocity over time, or final velocity minus initial velocity over time. What are the units of acceleration? Meters per second squared. What are the units of time? Seconds. And what are the units of initial and final velocity? Meters per second. So what we're going to do is combine those two equations together to make a new equation which links the resultant force, which is up here, so the resultant force, which is over here, to the change in momentum, which is going to be a combination of this mass and this change in velocity. So let's see how we do that. So we start with the equation F equals ma, and then we substitute to where a is this expression for a. So that means F equals m times v minus u over t. That means F equals, if I multiply out this bracket, mv minus mu over t. Now, mv is the initial velocity. mv is the final velocity. That's the final velocity. That's the final momentum, not the final velocity. And mu is the initial momentum, starting momentum. So by putting the equation for acceleration into the equation for Newton's second law, F equals ma, we now get this equation which says F equals final momentum minus initial momentum over time. Now the final momentum minus the initial momentum is the change in momentum. So that's the change in momentum over time. And this is the equation which links resultant force to a change in momentum. Another way we could write it is force equals, and then we could split change in momentum up into the mass of the object times the change in velocity. That's exactly the same equation. So that's the equation which links resultant force to a change in velocity. So we can see that a bigger change in velocity needs a bigger resultant force, but we can also see that there's an inverse proportionality between resultant force and time. So there seems to be something here about if you've got a bigger time, that means a smaller force, or if you've got a smaller time, that means a bigger force. We'll look into that a bit more later on in the video. Let's try some examples using this new equation. So using the equation, force equals change in momentum over time, which can also be written as mass times change in velocity over time. Pause the video and try this question. Press play once you've done it. You should have now tried this question. So let's go through it together. So we start by finding the change of momentum of the object. So to find the change of momentum, we need to find the final momentum minus the initial momentum. So the final momentum will be the mass times the velocity at the beginning. So that's 1,560 times, we don't know the velocity at the beginning. So this question here is one which previously you would have answered by working out the momentum at the start, working out the momentum at the end, and finding the difference. But we can't do that here. So clearly we need to use this new equation. So let's use the new equation. So we've got force equals change in momentum over time. So here we have a force of 3 kilonewtons. What's that in newtons? Say your answer to the video. That's 3,000 newtons. We have a change in momentum which we don't know. And what's the time here? 3 seconds. So let's substitute those numbers into the equation. So we've got force, 3,000, equals change in momentum over time. Let's rearrange. So we've got 3,000 times 3 equals the change in momentum. So that means the change in momentum is 9,000. What are the units for momentum? Kilogram meters per second. So there we go. That seems to be another way of working out a change of momentum if you do the force times the time. That's actually called impulse. It's not something we're going to look at in the GCSE, but that is the change in momentum. So using the equation, we've put in our resultant force on our time, and we've been able to work out the change in momentum. Now that we know the change in momentum, we can do part B. So if it was originally at rest, that means its original momentum was what? 0. Its change of momentum was 9,000. So what's its final momentum? 9,000. So we can therefore use the equation, momentum is mass times velocity, to find the velocity after 3 seconds. So the mass is 1,560. The velocity is what we're trying to find. So the velocity will be 9,000 divided by 1,560, which is 5.77 meters per second. So the main novelty of this example was we found change of momentum by using the resultant force and the time, which is something that you probably haven't done before. Let's do another example now. So pause the video and try this question. Press play once you've done it. You should have now tried this question. So we need to work out the one that needs a bigger resultant force to stop. So we're going to use the equation. So let's do it first for the lorry. So force is mass times change in velocity over time. So for the lorry, its mass is 3,500. Its change in velocity is 3 because it's going to be fully stopping. And the time that it does that in is 1.5 seconds. So using a calculator, 3,000 times 3 divided by 1.5 is 7,000 newtons, or 7 kilonewtons. For the car, we use the same equation. F equals mass times change in velocity over time. The mass of the car is 1,200. The change in velocity is 4. Time is 1.2. Using a calculator, 1,200 times 4 divided by 1.2 gives 4,000 newtons. So even though the car was moving faster and stopping in a shorter time, its mass was so much smaller than the lorry's that the lorry needs the bigger resultant force. So let's look at some conceptual stuff to do with the idea that force is inversely proportional to time. So if you look at this equation here, resultant force is change in momentum over time. That tells us that resultant force is inversely proportional to the time. Let's look at that with some numbers. Let's say you have an object, and that object is going to experience a change of momentum of 1,000 kilogram meters per second. So let's say, for example, a car crashes into a wall, and suddenly there is a change of momentum of 1,000 kilogram meters per second. Let's say that change of momentum happens over 2 seconds. What will the resultant force be? Work it out. Say your answer to the video. Well, it will be 1,000 divided by 2, which is 500 newtons. Let's say instead that we make that time 4 seconds. So we've doubled the time. Use the equation to work out the resultant force now. So this time it would be 1,000 divided by 4, which is 250 newtons. What has the time multiplied by here? How much bigger is 4 than 2? It's 2 times bigger. And what's happened to the resultant force? It's divided by 2. So that's what we mean when we say that resultant force is inversely proportional to time. By doubling the time for this change of momentum to happen, we've halved the force. In fact, if we were to multiply the time by 5, that would reduce the force by 5 times. The force would divide by 5. If the time was divided by 3, the force would times by 3. So we can use this to make safety devices. So imagine you're in a car, and so here's a car, and you're driving in the car, and unfortunately you crash into a wall. So here is a wall. Now, when you crash into the wall, firstly, the car's going to stop, but you are not, because you are not part of the car. So the car will stop because the wall's in the way, but you have inertia. You have inertia. Newton's first law applies to you. Newton's first law, as we said earlier, says that objects will continue at a constant velocity unless a resultant force acts. So this resultant force is acting on the car, stopping the car. You are just going to carry on moving forwards. Also, anything in the car that's not attached to the body of the car will also carry on moving forwards. And if the car stops very, very suddenly, that means you or whatever objects are loose in the car are going to slam into the steering wheel or onto the dashboard or into the front window. So the idea is the car stops, but the things inside do not. Things inside carry on moving forwards. That also counts for, let's say you'd left a cup on the top of the car. So let's say you'd got a takeaway, you put the cup on top of the car to do something, you forgot all about it. As soon as you just press the brakes or something, that cup is going to fly off the car. In which direction would the cup fly off the car if you were to suddenly brake and there's a cup sitting on top of your car? Say your answer to the video now. So a lot of people naturally think the car would fall off the back of the car, but actually the cup will fly off the front of the car because the cup is going to carry on going, whereas the car is going to stop. So the car stops, the cup carries on moving, so the cup falls off the front of the car. So what that means is we need to have some safety features which can cushion that blow. And what does cushioning mean? Well, let's think about an airbag, for example. What an airbag does is it doesn't stop the fact that you need to fully stop. If the car has stopped, you are going to fully stop as well. So it doesn't affect the change of momentum. So what an airbag does is it increases the time for you to stop. So there's going to be a large change of momentum. So there is a large change of momentum. You can't get away from that. You were moving very fast and now you're not because you've crashed into a wall. So there is a large change of momentum. But what the airbag does is the airbag increases the time for that change of momentum to happen. It increases the time for you to come to a stop because it's a cushioned surface. So instead of stopping instantly, the moment your head hits the dashboard, the change will be a bit more gradual. Maybe instead of stopping in 1/10 of a second, you'll stop in 1/2 of a second. That's 5 times slower. And that's going to reduce the force by 5 times. So the airbag increases the time for the change of momentum to happen. This decreases the rate of change of momentum. So rate means what in physics? Say your answer to the video. The word rate always means per second. So it's kind of how fast something is happening. So if your time is being increased, so if the airbag is making your change of momentum happen slower in a longer time, that's going to decrease the amount of change of momentum you experience per second. Look at this equation over here. This says resultant force is your change in momentum per second. Resultant force is your rate of change of momentum. In words, this equation says resultant force is rate of change of momentum. So by increasing the time for the change of momentum to happen, you decrease the rate of change of momentum, and that therefore decreases the force. And that reduces the chance of injury and death. Now, this is a nice physics concept because we explain it conceptually in words, but we're using an equation to justify it. So at some point in this answer, it's also worth saying because resultant force is change in momentum over time. And that shows you that there's this relationship, the bigger the time, the smaller the resultant force. So this answer here is the answer to the question, why do airbags increase vehicle safety? Why do seatbelts increase vehicle safety? Seatbelts do the same thing. A seatbelt will stretch a little bit. So instead of stopping instantly, you'll stop gradually. The seatbelt will also probably prevent you from smashing your head into the headboard or the window. Any cushioned surfaces, so any kind of sand surface or soft gym mats in a gym, or any kind of crash helmet or any padded armor if people are doing various sports, all of this stuff, all of these cushioned surfaces help in the same way. So just pause the video and read the explanation again. Press play once you've done that. So you should have now read this explanation again. This explanation is the answer to every question about cushioned surfaces. So why are the floors of playground soft? Well, if a child were to fall off a swing, there would be a large change in momentum. The cushioned ground increases the time for the change of momentum to happen. This decreases the rate of change of momentum, therefore decreases the force. This reduces the chance of injury. It's the same every single time. So that is the answer to any question about how do these soft surfaces reduce injury. So let's go back to our egg demo. So if we have our egg, and here's the other egg, this egg is landing on a hard surface, this egg is landing on a soft surface. What is the reason that this egg will crack and this egg will not crack? Pause the video, write down what you think, press play once you've done that. You should have now written down why you think the egg which lands on the hard surface cracks and the egg which lands on the soft surface does not. And the answer is that when the egg lands on the soft surface, there is a increased time that causes a decrease in the rate of change of momentum, and that decreases the impact force. Whereas on the hard surface, it's exactly the opposite. On the hard surface, there is a decreased time for the change of momentum to happen. Let's add that in, for the change of momentum to happen. So for the hard surface, there is a decreased time for the change of momentum to happen. That increases the rate of change of momentum, and that increases the impact force. There's a very, very clever bit of engineering with cars which uses this idea. So the front of cars, modern cars, they just crumple as soon as there's an impact. And this causes cars to be complete write-offs, and the car is completely destroyed and can't be used again, but it protects the people inside. So what happens is, if this car were to crash into a wall, the whole front of the car would just crumple. So the whole thing would just crumple up. So the car would end up almost like embedded in the wall. So the front of the car has just completely crumpled and collapsed. But what that does is it means that instead of the car just hitting the wall and stopping instantly, which would happen if the front of the car did not crumple, if the front of the car just stayed solid, the car would hit the wall and it would just stop immediately. Whereas with this crumple zone, the car does not stop immediately. In the time it takes for the whole front of the car to crumple, the car carries on traveling a little bit of distance. That takes a bit longer, and that decreases the impact force. So crumple zones work exactly the same as soft surfaces. What a crumple zone does at the front of a car is, when the car crashes, the front of the car crumples and just collapses. That increases the time for the change of momentum to happen. That decreases the rate of change of momentum. That decreases the impact force, reducing the chance of injury and death to the people inside the car. Really, really brilliant engineering. You destroy the car, but you protect the people inside. Please pause the video to do these questions. Press play once you've done them. You should have now done these questions. Pause the video to mark the first 4. Press play once you've done that. You should have now marked and corrected these first 4 questions. Please pause the video to mark and correct the rest of those. Press play once you've done that. You should have now marked and corrected these questions. Pause the video to do these questions. Press play once you've done that. You should have now done these questions. Pause the video to mark and correct. Press play once you've done that. You should have now marked and corrected. Pause the video to mark and correct these. Press play once you've done that. You should have now marked and corrected these. Pause the video to do this last question. Press play once you've done that. You should have now done this last question. Pause the video to mark and correct that question. Press play once you've done that. You should have now marked and corrected that question. In summary, we've learnt that resultant forces cause acceleration and therefore cause changes of momentum. But if that resultant force acts over a longer time or a shorter time, that can change the size of the force. So if a certain change of momentum is going to happen, for example, if somebody has fallen off a swing and lands on the ground, if the time for their impact is big, the resultant force will be small. But if the time for the impact is small, the resultant force will be big. there is an inverse proportionality between the time of the impact and the resultant force acting. And that leads to safety features on cars like airbags, seatbelts, and crumple zones, which all work by increasing the time for the change of momentum to happen, therefore decreasing the rate of change of momentum, therefore decreasing the force, thereby reducing the risk of injury. I hope this video was useful. Please like and subscribe for more videos on GCSE physics.